Okay, I think I can start to Start this session. Uh, Hello, everyone. Good morning, good afternoon, good evening to everyone wherever they are attending this webinar. I am Ali Rahman, hosting a pavement webinar series and an initiative which is recently launched at Southwest Jiaotong University to aim at enriching our academic environment by inviting and connecting with distinguished international scholars, researchers, and experts in different field or various fields of pavement engineering and materials to share their insights and expertise as a speaker in this webinar series. And the core objective of this initiative is to expose our students, researchers, and faculty alike to the forefront of research and the latest advancement in pavement engineering materials and pavement structure through this pavement webinar series. In Today we are launching the fifth episode of this webinar series, and the title of today presentation is microscopic and spectroscopic investigation of bitumen aging. And our today speaker is Professor Hinrich Grothe from Vienna University of Technology, TU Wien, in Austria. Dr. Hinrich Grothe is a full professor in physical chemistry of the atmosphere at the Institute of Materials Chemistry at TU Wien. He was trained in chemistry at the Leibniz University of Hanover, Germany, where he earned a PhD in low temperature chemistry. He had research estates also at University of Oslo and at Virginia Tech. Dr. Grothe's current research interests involve the examination of bitumen surfaces using various physico-chemical methods such as fluorescence and infrared spectroscopy and different microscopic techniques to investigate bitumen long-term aging. His work focuses on understanding the hardening and embrittlement of bitumen, which can lead to reduced resistance against cryogenic cracks and premature formation of fatigue cracks in bituminous layers. Dr. Grothe is an important contributor to the European Geosciences Union, where he is the science officer of the section Atmospheric Chemistry and Aerosols, and he's an editor of the Journal of Atmospheric Chemistry and Physics. So thank you so much, Professor Grothe, for accepting our invitation. It's a privilege to have you in our webinar series and today for your speech. And before I give the floor to Professor Grothe for our audience, I would like to mention that after a presentation, we will have a Q&A and session. So you can raise your hand and turn on your mic directly and ask your question, Professor Grothe, or you can, during the presentation, type your question in the chat box, and I will read the question, and Professor Grothe will answer our questions. So with that, I welcome Professor Grothe. Thank you so much, Professor Grothe. I give the floor to you. Thank you.
Yeah, thank you very much for this nice introduction. And of course, it's a pleasure to speak at your webinar. I will now try to share my screen with you. Let's hope that it works fine. And okay. Okay, we have the same problem again.
Yes, we can see now. Yes, now it's
You
appear,
see?
shows.
Okay,
Yes, we can see.
wonderful.
Yes, we can see.
You can see. Okay, now
Yes.
hopefully you can see the full screen now.
The full screen now? No, it is not full screen, but
Maybe like this.
uh, yeah, it's still not full screen. We can see the whole slides and the first slide.
Okay, sorry. I have no idea how to change this. Do you think it works, or shall I try again?
Yeah, I think that's fine. That works. It's okay now. I think yeah, we can.
Yeah,
Yes, we can continue.
because
Yes, thank you.
I see my full screen. I cannot see what you see, of course. Okay.
Is it on the
Anyway,
web? On okay, yeah. It is on web version or not the software version?
um, it's
Yeah.
now on the software version. Yeah.
Oh, okay, okay. So I think maybe there are some other, but it's okay, no problem. I think we can see. Yeah, we can see anyway. Thank you.
Okay. Okay, then thank you again for the introduction. And yeah, well, I will speak about microscopy and spectroscopy, and we are investigating bitumen and the aging of bitumen. As you certainly know, bitumen is a binder in asphalt. So in general, my research group is investigating the physical chemistry of atmosphere materials interactions. So on one hand, we have quite some projects which are focusing on the atmosphere, and we have many other projects which focus on materials, on wooden materials, on bituminous materials, and we are very much interested to learn how the atmosphere is impacting materials, and this finally is leading to aging, and that's important for the lifetime of materials, and which is a quite important matter at the moment, because the longer a material stands, the longer an infrastructure stands, the better, of course, is a carbon footprint of these infrastructures. Well, I will today speak about the results of our Christian Doppler laboratory, which is a national funding. And in this project, we focus on the interaction between structure, chemistry, and mechanics of the binder of the bituminous materials. So we are investigating structure with microscopy, the chemistry with spectroscopy, and the mechanics with rheology. And it's very interesting to see this intersection of all the three.
Sorry,
And
Professor
yeah,
Grothe, I'm wondering whether your slides are moving or not, because it
yeah.
is on the first, it is still on the first slide.
Okay, so we have a problem. Okay.
Okay, so maybe it should, oh yeah, now we can, yes, now it's moving. Yeah, it is this, now it is, okay,
I share again.
okay.
Wait a moment. So you should see the slide.
Uh,
No. Okay,
no,
let's.
yeah, it is on the first slide yet, and
Okay, I think I stop this and I make that again. Um, okay. So we have different reporter.
mhm.
Do you see my screen or not? No.
No, there's no screen, no.
I'm very sorry, but
No, it's okay. Yeah, this problem usually happens. No problem. Even if it is not possible, you can, I think, share.
you
I
see my
mean,
screen now?
no, no, still no.
Dear, what is wrong? It's not shared. But it was working when we were trying it, didn't we?
No.
Try it. Do you see anything now?
Let me see. Yes, we can see. We can see your screen, but not full screen, of course.
You see this change of the slides?
No. So maybe manually, I think manually you can. Oh yes, now it's moving. Now I think maybe manually should be like, yes, now it's moving. Yes,
But
yes,
the
yes. Now it's
presentation
moving.
itself.
Yes. Yeah, manually moving.
You can see it now?
Let me
Because
see. Yes, yes. Now it's full screen. Yeah, now it's full screen.
okay, wonderful. Okay. Okay, then let's start again. So
okay, yeah, that's good. That's good. Okay, thank you.
okay. So my talk is about the interaction between the atmosphere and our materials, and we are interested in structure, chemistry, and mechanics. And well, in this project, we are looking for the aging, and we are simulating the aging, and then we are doing chemical and mechanical analysis, and the final aim is restoration and also prevention of aging, as a restoration of the material and prevention of the aging. So let's talk a little bit about the bitumen. Bitumen, as you certainly know, is a mixture of thousands of different organic molecules. And bitumen is a natural, or can be a natural material, but the modern bitumen, which we use for road construction or roofing membranes, this is a product from a refinery from crude oil. And the application of bitumen is manifold, and the most important one, with about 85%, is just roads, pavements, airport runways. And here we have the mixture of bitumen and the mineral aggregates, which form the asphalt layer. The other important application is roofing membranes. About 10% of bitumen goes into that. And here, very often, it's in a mixture with different kind of polymers, with SBS or APP. And only 5% are used for sealing applications. So that means for coatings and paints, and also here polymers are added. So the desired properties for our bitumen is that it is adhesive, has a viscoelasticity, which is very important, and it is waterproof, and it's quite chemical resistant. But as I will show you, of course, it can undergo aging. And the chemistry in bitumen is very broad, but from the components, it's mainly carbon, hydrogen, nitrogen, oxygen, sulfur, and there are traces of metal elements like vanadium, for example, which plays quite an important role. And of course, we are very much keen on learn about this broad variety of organic chemistry inside the bitumen. There are aromatics, there are aliphatics, and there are different chemical compounds, which very often are not really well organized just through the broad variety. So one thing what we do is we apply so-called SARA fractionation. This is polarity chromatography. And by polarity, we can define our bitumen into subgroups. So first of all, we separate the asphaltenes, and then we run the SARA fractionation, and we receive saturates, aromatics, resins, and asphaltenes. And we use here so-called mini SARA. It's a special procedure which has been developed by Amit Bashin and his group. And it's very practical because we can use a special kind of solid phase extraction cartridges. And you can see the device on the right-hand side. So when separating the bitumen into its fractions, then it becomes easier to apply different kinds of spectroscopy. And I will show you today results from UV-Vis fluorescence, from infrared spectroscopy, from EPR spectroscopy and NMR spectroscopy. Why is this so important to apply these kinds of spectroscopy? Because we want to understand aging. And aging is a problem because aging forms material failure. There are potholes, cracks, and many problems with the road. And of course, it's dangerous if you have cracks and potholes in your road. You have a problem with the waste. It's also a waste of money. And you have environmental problems because you are generating volatile organic compounds. There's aerosol formation. And finally, there can even be water contamination due to leaching. So it makes sense to understand aging. And what we try, and not only me, but many groups try to do laboratory aging. But laboratory aging, as I want to show you, is different from field aging. What are the differences? Here is a comparison with a so-called pressure aging vessel test. This is a standard aging method. And the difference is, for first of all, temperature. On a road, you have a maximum of maybe 70 degrees C. But in the pressure aging vessel test, you have 90 to 110 degrees. So the temperature in the laboratory is much higher. Then on the field, of course, you have 1 atmosphere, but in the laboratory, you have 20 atmospheres. On the field, you have 20 years. In the laboratory, of course, you want to do things in a shorter time. So you have only 20 hours. And the main difference, of course, is that in a field, you have the troposphere, including reactive oxygen species, light, while in the laboratory, you handle your sample in the dark and with compressed air. So it's not the same, but of course, we need laboratory aging because, we normally don't want to wait such a long time, and we want also to make predictions about the resistance of our material and to learn about our material. So it's necessary to do lab aging on a shorter time scale, but at the same time, it's also important to keep the parameters which are so important in the field also in the laboratory. So the motivation is we want to have a thorough assessment of chemical aging. So we want to develop a chemical model to understand. We are going to set up a device which can simulate aging, and I will later on talk a little bit more about this. And the final aim is, of course, to conceptualize products that withstand aging processes. Okay, so when talking about aging, we can differentiate 2 processes. The first process is the short-term aging. This is what happens just at the beginning. During the production, in the mixer, there's a lot of contact with the air, with moisture, but also the temperature is quite high. It's about 160 degrees during the production of the road. Later on, during the next 10 to 20 years, when the road is used, there's the so-called field aging. That's the second process. And here we have a contact with air, but also with the reactive oxygen species like ozone, NOx, OH radicals. Moisture, of course, the radiation, the sun radiation, temperatures of maybe up to 80 degrees. And there is, of course, mechanical stress due to the use of the road. So here we want in particular focus on these reactive oxygen species, which you see on the right-hand side, and which are in an equilibrium also with the light and also with evaporation of volatile organic compounds. So let's talk a little bit about the troposphere and these reactive oxygen species. The main components are ozone, nitrogen oxide and OH radicals. And they are formed in the so-called photosmog, which happens during daylight. And here is just such a tropospheric cycle for the OH radical, and I will try to explain that a little bit to you. The whole story starts with the NO2. The NO2 is a radical, and the NO2 is emitted, for example, from combustion engine, but there are also known natural processes which produce NO2. The NO2 reacts with the light and is cleaved, and so you have nitrogen monoxide and oxygen atoms in a ground state. The oxygen atom then reacts with molecular oxygen, form ozone. The ozone reacts with light, forming oxygen atoms in an excited electronic state. And this oxygen then reacts with water, with humidity, and form OH radicals. And the OH radicals are very important substance. They are considered like the soap, the washing powder of the atmosphere, because the OH radicals attack all kinds of organic materials. And so the OH radical can oxidize hydrocarbons in carbon dioxide and water, abstracting hydrogen atoms. And these hydrogen atoms then in turn can react with molecular oxygen, producing HO2 radicals. And this is very reactive chemistry. And these HO radicals then react with the NO and very quickly oxidize the NO back into NO2, and then you can start the whole cycle again. So a very crucial process in all this is, of course, the formation of the OH radicals. And for this, you need oxygen atoms in an excited electronic state. What does it mean? This is the oxygen atom, the electronic configuration on the left-hand side. And you see how the electrons are filled in the atomic orbitals. And you recognize that there are two p orbitals, each with only one electron, and they are in parallel. So this is a triplet state. But they can also be only in one orbital, then they are antiparallel, or they can also be in two different orbitals, but also have different spins. So they are also antiparallel, and this is called both the singulate state. And the singulate state, this is the electronic excited state that's more reactive. And this is then reacting with moisture. And to generate these excited electronic excited oxygen atoms, you need light below 310 nanometers. So you need near UV light, and this is important to run the whole chemistry, the whole tropospheric cycle of the OH radical. And this, of course, is very important also for the oxidation of our bitumen. In general, NO2 then reacts with OH radicals, and finally on a surface, like our bitumen surface, like the road surface, but also many building surfaces, you have the formation of HONO, which is an important intermediate. So this is quite complicated atmospheric chemistry. And for us, it's important to understand that we need oxygen, nitrogen oxides, and light in order to finally understand the oxidation of our material. Okay, so then let's return to what I said already. We have the short-term aging and we have the long-term aging, and in particular the long-term aging, which goes through the whole lifetime of our road, is very important. And within this, it is the reaction of radicals and light and the oxidation of aliphatic and aromatic compounds. And as I said, the temperature is different at the beginning, but then the temperature is restricted up to about 80 degrees. So this graph here is viscosity against time. But what is more important for us is to see how the oxygen is incorporated into that material, how the polarity is changing, how the material is chemically altered. And for that, infrared spectroscopy, for example, will give a much more interesting result. So we have fast change during the asphalt production, and we have a slow increase during lifetime and a correlation here between viscosity and time, but as I will show you later, also a correlation between oxidized organic matter, which is mainly carbonyls, but in some cases also sulfoxides formation and time. So how to investigate these changes? This is just the electromagnetic spectrum, and where you can recognize that the visible part is only a small fraction. But in the visible part, we can do UV-vis spectroscopy, we can do fluorescence spectroscopy. With longer wavelengths, we can do infrared spectroscopy. That means we can observe the vibrations, the characteristic vibrations of our moieties inside the material. Then we can go further with the microwave radiation. We can run EPR spectroscopy. That means we can recognize the spin of our electrons, of our free electrons in the material. That's important because we talk here about radicals, for example. And finally, we can also look for the nuclear spin. That means we can do NMR spectroscopy. And all these different spectroscopic techniques we have at hand, and I will show you some results. So information we want to gather is molecular size, aromatic systems, aromaticity, functional groups, fluorophores, and organic chemistry. The whole bitumen chemistry is in our focus. The techniques we have at hand, as I said, are different NMR techniques listed here in the first line, EPR spectroscopy, FTIR spectroscopy, which we run here in the attenuated total reflection mode, and then UV-vis and fluorescence spectroscopy. So the result we are longing for is the molecular characterization of the bitumen, finding and developing methods for proper assessment, and the analysis of field aging processes. So evaluation of what is really going on with our material on the road. And we, of course, want to apply a kind of chemomechanical toolbox. So that means we also want then to correlate our chemical findings, that means our spectroscopy, with microscopy and with rheology. And finally, we want to break that problem down and developing and improving aging simulation devices. Okay, as a good example, let's have a look on the infrared spectroscopy. In infrared spectrum, this is rather simple. You recognize here in aliphatic signals, you see aromatic signals. But in general, the infrared spectrum of the whole bitumen gives not really a lot of information. But if you apply here SARA fractionation, that means if you apply this chromatography, polarity chromatography, which I was speaking about before, you see that different fractions. You see the saturates, the aromatics, the resins, and the asphaltenes, and they give different infrared spectra. So now the situation becomes much more clear, and you get a much better spectra and much more chemical information after the separation in these four fractions. And so that's an important thing, because now you can really recognize different functional groups, and you can, for example, also see if you have smaller aromats or larger polyaromatic systems. And you can also see sulfur oxides, and for example, you can also see alcohols or OH functional groups. And this is quite interesting. This is a magnification of the OH stretching mode. And in the infrared, of course, you already see differences. You, for example, can recognize that in a saturate fraction, you see no OH groups, and then you can see the differences between the other fractions. But it's not very detailed information. A more detailed information I can gather with NMR spectroscopy. And this is a special kind of NMR spectroscopy, because here you react the OH functional group with a phosphor compound, with TPM-DP, and you form a phosphor ester, and then this phosphor 31 is NMR active, and by this, then you can really differentiate different alcohols and acid groups and their position within the material. So this is a very interesting technique, because you, first of all, you can correlate infrared spectroscopic information and NMR information, and you can very much, in particular, focus on OH groups and learn where exactly they are situated, and you even can try to quantify that. So spectroscopic assessment brings us information. We can look for functional groups, and we are longing for to understand how many aromatic groups, for example, are there, and to understand how these aromats are organized, if this is a polyaromat or if these are smaller aromatic systems, and then to quantify that. And here, not only infrared spectroscopy is helpful, but much more fluorescence and NMR spectroscopy are used. And here again, on the left-hand side, you see the fluorescence of the different fractions. And you see also the different spectra. They are really different for these different fractions because the size of the aromats are changing, and it's mainly the aromatic system or the conjugated olefins which are producing the fluorescence signal. So the larger the system, the conjugated system is, the more the system is shifting, or the answer is shifting to longer wavelengths. And this is what is shown here. And here we can correlate this information then with different kinds of NMR spectroscopy. This is correlation NMR spectroscopy, and you might recognize that here you can really nicely differentiate saturates, aromatics, olefinic systems, and aromatic systems. And you can correlate that with your knowledge from the fluorescence, from the infrared, and we can really learn and understand the chemistry inside this material. And as I already said, the higher polarity then means more aromatic groups. And this is finally what we learn from the system. And then there's another NMR technique, which is called DOSI, diffusion ordered NMR spectroscopy. And here we can even see the molecular sizes of the molecules inside our materials. Again, we have the 4 fractions: saturates, aromatics, resins, and asphaltenes. And you see on the right upper corner the different spectra gathered with these doses. And you can really see that they are different in size. And you can learn a lot. So you have the functional groups, you have the size of the molecules, and all that together gives you an interesting picture. Okay, then let's have a look on the fluorescence into more detail. This is a special kind of plotting the fluorescence result. On the y-axis, you see the excitation, and on the x-axis, you see the emission. So you have to imagine this like a map. Yeah, it's a 2D plot, and the different colors give you the different intensities. And by looking on excitation against emission, you can see at which wavelengths you get a highest intensity in your molecular system. And this here is focused on the resins. And of course, you can then also just have a not a map, but a normal fluorescence spectrum. And what we have learned here from this kind of fluorescence spectroscopy of the resins is that we have quite an interesting compound here inside, which is the porphyrines. And these porphyrines are chelating metal oxides. And a very important metal inside bitumen is vanadium, and vanadium forms vanadium oxide. So the vanadium oxide is complexed in these porphyrines. And one idea is that this might play an important role also in the aging processes, since this is very prone to absorb light. So then knowing about the porphyrines from the fluorescence, we had a look on the vanadule of the vanadium oxide, which is active in the EPR because it has a free electron, the vanadium here. And you see also here the EPR signals, which correlates then with the fluorescence signal and really shows us that these complexes exist and that we can learn about the organic radicals, the vanadium oxide, the porphyrines, and how they behave during aging. To sum that up a little bit, we are doing a spectroscopic assessment, and we are looking for the determination of the main oxidation products. We are looking for fluorescence properties, intensity, and emission, and we can try to define parameters like the minor oxidation products, the nitrogen-containing products, the evolution of the aromatic system, and the organic radical content. Here I have shown you with the EPR spectroscopy. So we were performing studies on the aging, and we were not using the pressure aging vessel test, but we were developing our own system. It's a Vienna binder aging. And the difference really is that here we can apply reactive oxygen species. That means we are using nitrogen oxide, we are using ozone, we can even apply light, form OH radicals if we want, and we can change temperature. We can control and analyze the gas phase very sufficiently and see concentrations. And we can change humidity. And finally, of course, we can bring that sample then to our different kinds of spectroscopy. So this is a so-called VBA aging cell. We can do thermal aging, but we can also apply this reactive oxygen species. And this is the new point in it, because other aging tests on the market have this chemistry, the chemical changes not available. So we see efficient simulation of field aging. We can change the parameters, as I already said, temperature, ROS, humidity, and we monitor mechanically and with spectroscopy and see the changes. So just to give you an example, with the EPR, we determine so-called EPR ratio. That means we record the organic radicals and set that into relationship to the Vanderduel signal. Why we have chosen the Vanderduel? Because this is not changing during aging. So this is our standard, if you want. And when you do so, you see the unaged sample on the left-hand side. You see short-term aging, and then you see temperature changes. You see then temperature changes under nitrogen in comparison to oxygen. And the moment when we apply oxygen species, so the ROS, we can really recognize that this EPR ratio is growing a lot. So the formation with OH radicals, with NOx, with ozone, is generating radicals in our material. That's an important message. And also there are differences, of course, depending on the binder. It's mainly the viscosity of the binder, which is important. And also here it's a comparison between reactions just with nitrogen, which is inert, and then on the other hand, applying an oxygen-containing atmosphere where ROS formation is possible. And yeah, we see that temperature has an impact. And because of the diffusion of the different molecules inside the material, and with higher temperature, it's easier to overcome reaction barriers, of course. And here is just an example. These are organic radicals, and these organic radicals, they can meet and they can form a new bond. And so it's a dimerization. This is typical for in the absence of oxygen, and can be observed with a spectroscopy. Okay, this is the chemistry. So then let's just look on the surface, because aging, of course, happens on the surface, and how surface morphology is changing. And one possibility to investigate the surface morphology is atomic force microscopy. And an atomic force microscopy gives us the possibility to combine that also with different microscopic techniques, as I will show you. So when we have an AFM picture, as you certainly know, there's a katana phase, there's a periphase, and there's a paraphase. The katana phase, that's the inner core of the structure. Around that is the periphase, and the matrix, if you want, is the paraphase. Many authors also call the structure B structure, because if you look on that in a two-dimensional way, it is looking a little bit like the stripes of this insect. If you, however, look with the atomic force microscopy, you recognize that these stripes, in fact, are three-dimensional. They are more looking like erected objects sitting inside that matrix. But you have also to understand that this topology is in a nanometer scale, while the two-dimensional plot here is in the micrometer scale. So this is a rather flat structure, but it's an up and down, and that's also why in Greek it is called katana. And we were applying atomic force microscopy in different modes, which is seen here on the right-hand side, and we were combining that with information from fluorescence microscopy. We already know that our system shows a fluorescence signal. We already know that the aromats are responsible for the fluorescence, and it's particularly the resins and the small aromats, which show a very strong fluorescence signal. And here we can really recognize that these materials obviously are clustering inside these morphologies, which we have already observed with the AFM. And then on the left-hand side, you just see conventional microscopy. And so we can characterize our system. We see that these so-called bees are about 4 to 5 micrometers long, and they have a height of about up to 5 nanometers. And there's a chemical differences. So it's not a homogeneous chemistry in that surface, but the structure has a different chemistry if you go from the inside to the outside, and the matrix is also chemically different. So we applied then a correlation of atomic force microscopy and mass spectroscopy. It's time of flight mass spectrometer in the SIMS mode, and you can really recognize here different molecules which have been analyzed, and then this information has been correlated with the AFM picture. And you see that the chemistry is really different on different spots. And then we were also correlating the AFM with the infrared. That's a own kind of spectroscopy where you actually are using the AFM as a detector for the infrared absorption. And this here is recorded at a band of 1080 wave numbers, and you can really see the heterogeneity of that surface. And this is an aromatic signal, and you can see that the aromats are not observed in the katana, but predominantly seen in the paraphase. And you can also do that, of course, with other bands, and then understand the distribution of different compounds in that atmosphere, and really learn how different chemical compounds are situated in the bitumen surface. So just to summarize that a little bit, we have the katana phase. This is up and down. This is the inner core, and consists of a few saturated hydrocarbons, functionalized matter, and a fraction of aromatics. Then we have the periphase, which is shows also a gradient and is made from aromatic and functionalized molecules and a small fraction of saturates. And then you have the matrix around the paraphase, which is made up mainly of polyaromatics and smaller fraction of carbonyls, esters, and ketones, and so on. And this can be all analyzed with infrared spectroscopy and the different surface techniques. And then the question, of course, is how is this changing then during the aging process. This is light aging, as been shown here on the left-hand side, and you can really see that the fluorescence microscope picture is changing, it's getting blurred, the structure is changing a lot during the aging process, also because the chemistry is changing. A lot of oxygen is incorporated in the structure, the gradient, the chemical gradient in the periphase is changing, and yeah, this finally is what embrittles then also this material. So we were running some light aging experiments, and we had light sources. We could apply different wavelengths. We could monitor with infrared fluorescence and NMR spectroscopy our light aged samples. And the questions we wanted to answer: which fractions are impacted? We were looking for rates, for structural changes, and for oxidation products. And here, this aging was done for 2 different binders and for all 4 fractions. And you can really see that saturates are only little altered, while it's mainly aromatics and resins, which shows a very strong change in this aging. And then with NMR spectroscopy, we can even quantify here. We can show where changes happen. And what is also interesting here to observe that the aromatic signal decreases during light aging. That's understandable on one hand side, but it's also a little bit contradicting what we observe with the infrared. And because at the infrared, we see the things a little bit different, but also here the 4 different fractions were oxidized and spectra were recorded. And yeah, as I said, we are correlating then with NMR spectroscopy, and we see that we produce a mixture of ketones, carboxylic acid and esters. And with the phosphor NMR spectroscopy, we can also see the carboxylic acids, alcohols, and we can quantify. And yeah, this is laboratory aging. So how does this compare then to field aging? So for this aim, we were setting up an aging field in Vienna, and we took regularly samples from that field, and the field is already 7 years old now. And then we had samples from a road, it's near Enns, and the samples are 17 years old. And then we were producing also short-term aged samples in a way that we just placed bitumen samples on the roof of our building. And again, we can run infrared spectroscopy, and we can run that infrared spectroscopy on all 4 different fractions, on saturates, aromatics, resins, and asphaltenes, and observe the differences in different windows. And we can see changes in alcohols in aromatic systems and in aliphatic systems. And we can observe the ketones and the amide bands. And we see an increase of the aromaticity. And as I said already, that's a little bit in contradiction to what we saw on the NMR. Yeah. And but it's interesting, and I will later on come back to that. So the other thing, what we did, we were also running fluorescence, and this is this kinone structure with the vanadiol. And also here we see that this is going down during the aging. You see the unaged signal, the short-term aged signal, and the field aged signal from a long time. And obviously these porphyrines are playing quite an important role inside the resins fraction. So to summarize that a little bit, the overall, as I said, in the NMR, we observe a little bit of different things than in the infrared in terms of the aromaticity. And we try to figure out that using also fluorescence. And fluorescence show us again that we have a shift in the asphaltenes. And of course, the polarity is increasing, the oxygen is taking up. You have intermolecular linkage to the asphaltenes, and we can then compare also those results gathered with a fluorescence mapping here with lab experiments and with field experiments. And we can also see the differences here. The upper one, this is the pressure aging vessel test. So this is a conventional technique. Then we have the Vienna binder aging, and it is different to what you observe with the puff. And then you see what we had from the field aging, so from this road really taken, the 17 years old sample. And that comes much more next to the VB aging than the pressure aging vessel test. And then we tried to correlate that with mechanical investigations, with rheology. So that's a DSR. So we can take a DSR measurements and correlate that with infrared. And okay, sorry, here we have obviously a little problem, but we can calculate for an aging index. That means we take the infrared bands, we are integrating those infrared bands and set a correlation between the oxidized, that means the carbonyl bands, and the difference between carbonyls and sulfoxides in relation to the absorption of the methyl band, which is not changing so much during aging. And this aging index we have plotted here with the G star value from the DSR, so the DSR against the aging index. And what can we observe? When we work here in our Vienna binder aging cell, just with pure nitrogen monoxide, there is not so much aging observed. It's much below the pressure aging vessel test. It's probably only thermal aging. When we apply NO2, it's also not so much reaction because it's NO2 inside nitrogen oxide. If we apply ozone, which is a strong oxidizer, we go beyond that already a little bit. But if we apply NO2 in air, this is really changing. And obviously, it needs, as a reaction mechanism, it needs a nitrogen oxide, which is a radical, but it needs nitrogen oxide in combination with oxygen. So we imagine that the NO2 is something like a door opener. It reacts with our aromatic structure, and then the oxygen can go into that hole and further oxidize the organic material. And this is a very typical reaction known for polyaromatic systems. So just to summarize that a little bit, we have an oxygen atoms. We have as a product mainly carbonyls and sulfoxides. Minor products are alcohols and acids. Nitrogen compounds are amides and porphyrines. We have structural changes. We have an increase in aromaticity. We have less fluorescent aromatic groups, as I have shown you, but we have a growth of the aromatic system. And probably they are attaching then to the asphaltenes. And eventually this explains also a little bit the difference between the NMR and the infrared result. And finally, we have a chemomechanical analysis, which shows us that the reactive oxygen species in a cooperative mechanism between nitrogen dioxide and molecular oxygen are mainly responsible to what we observe here as chemical aging. Finally, I would like to point out that we have patented a special scanner to have the possibility in the production process, but also on the construction side, to observe the age of the binder. And the idea behind is that we record the fluorescence signal, and we know that the fluorescence signal of aromatics and resins is going down in intensity. And so the scanner is observing this in a very easy manner, is observing on the 3 different channels the signal, and then is correlating this and gives you a parameter, an aging parameter by spectroscopy which then can be used to get a quick idea of if the quality is still okay or if quality has already been changed during the construction and the mixing of the material. Okay, so in total, I may conclude we have a broader assessment of chemical state by SARA separation. We have modern spectroscopy and microscopy. We have new methods to analyze field aging. Additional processes are observed. We have an adaptation of gained knowledge by the Vienna binder aging. More realistic aging procedure has been developed. And finally, I would like to thank our team in the Christian Doppler Laboratory and our collaboration partner, which is Thomas Rosenau from the BOKU, who was responsible for the NMR spectroscopy. And I thank you for your attention. Thank you.
Thank you. Thank you so much, Professor Grothe, for such a very inspiring and very insightful presentation, which is, I think, believe an overview of your current research, a very in-depth analysis of the bitumen aging and the processes, which is very, very, for myself, but very interesting and really open my eyes further to the really aging process, which is very, very complicated, I believe, process in the bitumen during the bitumen life. And yeah, I hope and with further research and deeper research in that field, we can really figure out one day how to really further postpone or avoid aging in our asphaltic roads.
Yeah, this is our final aim, of course. We are, of course, are looking for chemicals, rejuvenation, but also chemicals which just prevent the radical reactions of our material.
Exactly, exactly. That's true. Thank you. Thank you. So among the audience, if anyone has any question, you can raise your hand or you might type your question on chat box and I will read the question. Yes, Han Liu, please.
Okay, thank you for your excellent presentation. And I think it's very important and meaningful for the energy degree students. So I have a simple question. Why whether the RS aging or field aging, it seems like create a link with the long-term aging, but does the RS aging can take a create a link or create linkage to the short-term aging?
Yeah, that's a good question. Thank you. Well, the short-term aging is probably a process which has, how to say, a lot of things, chemically speaking, happen just at the beginning. Yeah. So if you are able to produce your road in an idle manner, that means to keep that short-term aging low, to prevent humidity, to prevent too much mixing with air, then you can prepare eventually the idle road, which then also stays much longer, maybe 20 years or 30 years. What we very often observe is that when the production process of the road was not done in a correct manner, yeah. Very often it's the same material, it's the same people who prepare that road, it's the same company, but there's 1 kilometer which is aging very quickly. It's maybe broken after 5 to 10 years, and another part of the same road stays for 25 years. And the difference was, for example, that the workers were just increasing temperature of the machine by a few degrees. And as a chemist, you know, with every 10 degrees, reaction velocity is doubling. So they are just turning it higher because then viscosity is going up, and then it's easier. It's less viscous, and then it's easier to prepare, and it's easier to work, and maybe faster. Maybe at the end of the day, they are increasing temperature a little bit, and then this material is short-term aged, is pre-aged, and is maybe already old when the road is paved. That's a problem. Yeah, and so it's very important to monitor all parameters during the production process. Yeah, maybe also, as I tried to explain with fluorescence, but one important parameter always is temperature. Temperature has to be monitored during the whole production process. If you are overheating your sample, you are generating short-term aging, and you are, carbonizing your material, oxidizing your material.
Okay. Thank you.
Okay.
Thank you, Professor Grothe, for your answer. Yes.
So I will leave the chance to other people.
Okay. Yes. Okay. Any other question? Please. So until if other people might have question, I also have one question. Professor Grothe, you talk about so many different mechanisms or the components that might together result in aging in bitumen. For example, you talk about tropospheric cycle, which very has important, in fact, process effect influence on the aging. Or you also talking about porphyrin, which is attracting the lights, and it causes also the bitumen aging. So I want to know is how really we can, or is it there is a possibility that we can interrupt this kind of, for example, cycles or mechanism in the binder in the bitumen to further retard or at least postpone the aging in our bitumen? Is it possible? For example, when you talk about the tropospheric cycle, how we can interrupt? Is it possible? Is it doable to really interrupt this cycle to avoid, or for example, this is my question that.
Okay. Well, unfortunately, we cannot change the chemistry of the atmosphere. Probably, that's not really possible. And it is of course there's a difference between an urban area and a rural area. In urban areas, you have much higher NOx concentrations due to the traffic, and probably that also means more aging in urban areas. So, but in general, the atmospheric chemistry you cannot change, but you can change, of course, the chemistry of the bitumen. And this is something where we are just at the beginning, but one hypothesis is if the vanadiol complexes play an important role in the absorption of the light and maybe also in the interaction with the radicals, we might look for bitumens which have not so high concentration of those vanadiol complexes inside. It depends a little bit on the raw oil source, but well, we still have to test that, but that might be a key to longer lifetime. Yeah.
Okay, great. And so I think my understanding from your presentation was that we were mainly talking about the petroleum bitumen aging. So I want to know, for example, since now, as you can see, because of the sustainability and green pavements and using new materials such as plastic bitumen or these things, so how it will be it changed the vision of and what we are researching on bitumen aging, if there would be any fundamental changes in the aging mechanism in the new the kind of bitumen like plastic bitumen or new fiber nano materials that are being used or as a modifier in the bitumen.
Yeah, that's a very good question. Actually, we also have a project on that, on bitumen, on organic or biological materials. The idea behind is that if we all in the future will drive an electric car, then I mean refineries will change a lot. There will be less production of fuel, and when there's less rectification of raw oil, then we have less bitumen available, or the price is rising. So the idea is if we can take biosubstances, special oils, vegetable oils, and add them to our bitumen. Yeah, and this would also probably help to prevent radical reactions. At the same time, there are also projects which have the idea to completely substitute the bitumen. And as you said, we can use plastic waste. We can eventually also think about wooden products, polymers from wood industries. There are many, many different approaches. And I mean, since we are so much at the beginning, I can also not answer your question entirely, but it would be nice to see if a bio road would be accessible in the future, and maybe the lifetime will increase a lot. I don't know, but of course I hope for that. Yeah.
Okay, thank you. Thank you so much. I think they are very interesting, as you mentioned, very interesting. In fact, the question and that uncertainty that we don't know, or it is in the developing process that, okay, how this really gonna develop. And I hope we find any in the future, any opportunity or chance we can further or do some collaboration or academic exchange or research in this field, hopefully, thanks to your very rich experience and expertise in the field of the bitumen aging.
Yeah,
thank you. And I'm looking forward to that. Yeah, thank you. Thank you. Any other question among our audience? No other question? Okay. I think we are also running out of time, and so I think with that we can wrap up our today's webinar. Again, I appreciate Professor Grothe for his contribution and for his very nice and insightful presentation. Thank you so much again for accepting our invitation. It was a pleasure, great pleasure for me and my colleagues at Southwest Jiaotong University to have you today. And thanks also to our audience for the attending this webinar, and please stay tuned for our upcoming webinar.
Yeah, thank you again for the invitation. It was my pleasure. Thank you.
Okay, thank you everyone. Bye and have a nice day.